Hello. In this lecture, we're going to look at agent movement. So basically the idea of our game character that's controlled by AI moving around in the game environment. So we're going to look at a simple approach to movement, and then in future lectures, we'll look at more complicated movement. But we're going to have this material serve as a foundation for just understanding how a basic agent can move, and then we can move on to exploring other topics like path planning, and then come back to more complicated sorts of agent movement. So first of all, let's consider agent representation for our movement. So we really only want a representation for the elements of the game from an AI perspective to be as simple as possible, because that's going to make it easier to compute, keeping in mind that AI has limited resources to calculate anything that needs to be done. In terms of algorithms, you're having to budget what you're doing computationally for AI relative to graphics and audio and accessing the hard drive, network, and so on, depending on the type of game. So we want to keep things simple, only model what is necessary to support the task at hand, which is moving around. So part of that's going to be defining, well, where can the agent move? And so the first thing let's look at is, well, what type of movement does our game have? So one common type of movement that you see, especially with early video games, like some of the first examples of video games, would be classified as discrete movement. And so this conceptually would be something similar to checkers or chess, where you have a grid and there's different discrete locations. They're unique locations for your agent to move, and so there's not this kind of smooth, gradual sort of changing movement, which we'll see when we talk about continuous movement, but instead these very clear locations for the agent to be placed. So in this case, movement is very straightforward. It's easy to understand that you have these different locations, and that to move from one to the next is probably going to be based on some sort of rules regarding connections. Usually this is going to be adjacency. So like if you have a checkerboard, you can move from one grid cell to another adjacent cell. And there's different types of adjacency and so on. We'll look at some of this in more detail when we talk about path planning. But in terms of discrete movement, you've probably seen, well, certainly board games, but probably also video games as well that use this sort of movement. Mentioned before is also continuous movement, is like the alternative to discrete movement. And so in this case, rather than have different unique locations that our agent can be placed in, we now have the ability to move incrementally, small amounts. And so this is very common in video games that have more of like a real-time gameplay, arcade games, platforming games. So if you're moving like Mario around in a Mario Brothers game, you can nudge Mario forward just a tiny bit, or maybe make him walk rather than tiptoe or run. Again, depending on which of the games in the series you're playing, but all of them, I think, support continuous movement. So we have this discrete versus continuous movement that we can consider, and we might have different approaches for how we deal with movement in the two scenarios. So in the case of running either a discrete movement game or a continuous movement game, It's something that you maybe just intuitively know. You know it when you see it, sort of thing. But if we look like really carefully at the details, we might say, well, wait a minute. In a continuous movement game, you probably still have discrete locations that the character can move to. And so if you think about how numbers are represented on a computer, if you're using an integer or even a float, in either case, there's a limited resolution based on the bit depth of the data type. So even with a floating point, there's a fraction that you can't get any smaller than for moving the character slightly to the left or right, if we're, say, using numbers to represent positions. So you could say technically everything is discrete on a computer when you have fixed-sized numerical representation. So we maybe should think a little bit about, well, what do we really mean? And it's kind of hard to make a concrete formal definition of discrete versus continuous in the context of video game movement, but we'll try to at least have some rules of thumb to identify this. So for discrete movement games, we'll say that we have these distinct locations for the game objects to be placed, and they can these game objects can move around from each of these places in some human perceptually manageable number of locations. So for instance, a chessboard, you can look at a chessboard and you can clearly identify, okay, well, here's the different locations that a playing piece could be at. You might even be able to call out grid coordinates, like historical records of famous chess matches. You can just see the rows and columns listed to tell which pieces move. And also generally games that have this sort of discrete movement, you can't skip past adjacent locations. So if you want to go to the left, you're going to go to you're going to move your piece to the next most immediately left slot. You're not going to move some arbitrary number of pieces. Now you might have some different adjacency rules, like in chess. So the moving the knight, for instance, but it's still this well-defined adjacency information according to the rules of that playing piece. So you'll often also see discrete movement coupled with either turn-based time updates or slow automatic updates. So basically, maybe the simulation might update, and we'll take a look at how we might represent a simulation in a couple slides here. But every time the simulation updates with a discrete movement where it's not turn-based, you might have like something that is less than 10 frames a second. So if enemies are, for instance, moving around and you're moving the player around, it's very slow, kind of like tick, tick, tick sort of movement. And so that would still, that would be common of games, at least that I've seen, that have this discrete movement and positioning. And so also games with this discrete movement, usually the layout and representation of the world for the character to move in, it's motivated by gameplay rules. So like board game style understanding of movement and interactions of game objects. It's really just an abstraction that supports a particular type of gameplay, maybe like a strategy game would be an example. Now, in the case of continuous movement, though, we have distinct locations for our game objects, most likely just based on the resolution of integers or the number of pixels in a screen, or the resolution of a float. But whatever the resulting granularity is of these different distinct locations, they're so numerous that a human game player, they can't distinguish between one pixel and the next, or as they move their character around. So from their perspective, it's the same as moving an object around in the real world. You can't really precisely say where something is. I mean, you can measure with it with a ruler, tape measure, something like that, but there's always going to be some uncertainty in the placement of the object. And also, the movement that you see when an object is moving around in a game with this continuous movement is that you might, from update to update, might move a smaller or larger amount. And so this would be perceived as like a velocity. So it moves, if it's jumping multiple of these little tiny discrete locations, it's jumping these large distances, then probably you're going very fast, and if it's smaller amounts, it'll be slower. And also, will be coupled with a high frame rate supporting animation. So you have to hit some like this critical threshold of 10 frames per second for a human to perceive animation. Of course, most games you want actually much more than 10 frames per second, but at minimum 10. And so you can think in terms of round. You need at least a resolution of around the pixels on the screen to be continuous movement. And then lastly, the movement is motivated by physical realism and probably leveraging physics that you learned in high school. So like particle dynamics type physics movement. So in either case, whether we have discrete or continuous movement, you're going to have some sort of simulation loop that's running, and it'll, at a high level, it'll look something like what I have here on this slide. This loop, it includes the player, and so the player is observing the screen based on observations of looking at the screen, maybe hearing things from the speakers, makes inputs, so presses buttons on joysticks. This is sent to the computer, and an update process runs. So we're actually updating the simulation, and then whatever the result is. So like if you choose to move the character, that will happen. Now the update loop will also represent the AI processes. So any artificial intelligence updates for, say, an agent that's moving is going to take place during that update. And there'll be an internal measurement of how much time has elapsed. And so we'll get the rendering. Then we finally have this sleep or synchronizing state where maybe the computer just briefly waits before it begins the process again, over and over again. So for continuous games, we want this to be very quick, running at greater than 10 frames per second, usually at minimum shooting for 30 frames per second. So even a discrete game would run a loop something like this. If it's a turn-based game, there might be an interruption while we wait for an input, and then that would initiate the next turn. And in the case of turn-based or other sort of discrete game play, you might actually have to synchronize a separate I/O loop that's just handling the user interface that would be independent from your simulation loop, because you still want to be able to move the mouse cursor around, have feedback. If it's a game with a mouse, you might want to be able to bring up in-game menus and other things. So you'd actually have two separate loops in that case. But yeah, so you need to think in terms of, at least at a high level, you're going to have a loop something like this, where you're going to get little snapshots of time for your code to do what it needs to do for that moment. And then we'll go through the loop again, and you'll get another opportunity. So the sort of code that you write to support your agents, the movement, path planning, whatever activities your agents will be performing, they're only going to be able to think about the problem. If you imagine your AI code as doing the thinking, you're only going to be able to work on it for just a fraction of a second. aiming for something like 30 frames per second. You just have a fraction of a second to make a calculation and then let the system update. And then you're going to have an entirely new state of the world. Hopefully it hasn't changed too much, but it'll have changed some. Then you have to make entirely new decisions based on whatever data arrives. And that'll be influenced by the game player as they interact with whatever game objects they control. And also just the rest of the world's game world is going to change. Other agents are going to do things. There's physical changes occurring, like if you have physics simulation. So yeah, everything happens through this loop, and you need to make your agent code work with this. All right, so let's think a little bit about in a continuous world, the positioning. Now, back to discrete, it's pretty straightforward. You just, each of the locations is labeled in some fashion. So they're all represented maybe as a graph data structure, would be probably most likely how you would represent. And you just keep track like a reference to where the agent is to those positions. But in the case of continuous positioning, what we want to do is leverage our understanding of geometry. And so we're going to use a position vector that's relative to an origin. So we're going to have a coordinate system. And most often we would be working with a 2D coordinate space or vector space for our representation of positions in our game world. And so that's how we would go about saying like an agent is at a particular XY location in 2D. And so this 2D space is going to be made up of real number representations, so probably like floating point numbers in 2 dimensions, so an X and a Y. And these are basically scalars for our basis vectors. So orthonormal basis vectors, just your typical graph sort of layout where you have an x-axis and a y-axis. We'll actually find out it's more common to say x and z. We'll cover that in a few slides here. But that allows us to define locations, at least point locations. Now, our agent's not a point typically, but we'll also look at that in a second. So why are we using 2D? There's lots of games. You know, the modern sort of game is actually in 3D. You have 3D models. Think of something like Mario 64, like in the picture shown here. So that's clearly a game with 3D. But in terms of modeling for the purpose of supporting our agent movement, so the AI movement, it actually makes sense to think in terms of 2D. And one of the reasons why you might want to do this is, well, everything in the real world is, at least on Earth, it's bound by gravity, unless you're like flying around, say maybe birds or airplanes. So in terms of any kind of conceptual model for planning movement, it makes sense to just think in 2D. No point in complicating things. So we can actually get away with a 2D representation of positioning. And then in case where we do need to consider the third dimension, that can be just some special case logic. So for instance, jumping or falling, or maybe cases where we have multiple levels, we can have some special case code to like swap out 2D representations of multiple levels of floor plans of a building. And so this works out pretty well to just stick with 2D if you can get away with it. Now, if you have a game that involves flying spaceships around, clearly you would not force that to be 2D. So we would have to consider a different approach. But so let's just assume we have 2D for now. So next up, we need a way to represent our agent. Now, within the game, from the player's perspective, the character that the agent represents is not going to be a single point. But as we talked about before, with using position vectors, that's a great way to talk about locations in our 2D vector space. So we can actually simplify our agent to be a point, and then anything that's related to the agent's physical representation in the game, we can just synchronize that with this point. So as the agent makes decisions to move around the environment, we're just thinking about moving a point around the environment. When it comes time to consider something like, what does the agent collide with something, then in that case, we might consider an object centered on the point. And so we kind of change our perspective based on what problem in the video game we're trying to solve. If we're trying to deal with moving an agent around just the concerns of positioning, then we work with a point. And then when we're concerned with collisions or other aspects of gameplay, we make those decisions in relation to this point location. So therefore we can say that a game object or an agent is located at a point, and then we'll just carry along whatever metadata, whatever extra information we need, like a radius to know the overall size of the agent relative to the point. We'll just pass that information along in maybe a data structure. So let's consider a very simple movement scenario. We have an agent here that is seeking a target. In this case, we have a fish. So the agent needs to move towards the fish. In this case, we have a scenario with a continuous movement in a 2D game. So it's a real-time game, like you think of like an arcade game. So we have this fish that's flopping out of water, and we want the player to walk over to the fish. So how might we go about getting the agent to move in that direction? So we can assume we have a position vector. So the origin, we know an offset in X and Y that can place our agent. So we probably have something like this. And we can do the same thing, placing our fish. So, well, first of all, we're going to place points at the center of each of these different game objects, the agent and the fish. So they'll be at the center. And from there, we can figure out, well, where is the fish relative to the agent? We can just calculate a relative vector. So this is as simple as taking the difference of terms, so the x coefficients and y coefficients for those relative vectors. And you subtract where you're going to, you subtract where you're at from where you're going to if you want a directed vector. So in this case, the relative position vector A, where the fish is, you subtract from that the relative position vector B. So A minus B gives you the vector BA. So now we have a direction that the agent could go. So what we could do is, we could just add vector BA. So again, that's going to be two coefficients that tell us how to get from B to A. So we could just add that to the position vector B. So if we do that, that would mean that provided we update the game, like if we tell the game object that is the agent to now have this new coordinate, so that would be, again, B plus vector BA, then that would put the agent right on top of the fish. So that would instantly get the agent to the fish, and that probably wouldn't be what you want, though, except in certain games. So if you're not teleporting, though, you would, instead of going instantly, you will want to go in some kind of incremental fashion relative to the update loop. So think back to the loop that I showed before where we were polling user input, running the update process, rendering out to the screen and to the speakers, and then synchronizing and looping back again. So we need our algorithm to work in that framework. So one thing that we might do is say, well, all right, well, we've got vector BA. What if instead of going the full length of BA, we go some fraction of it, like maybe halfway down the vector? So we perhaps could just divide the two coefficients in half and then add that to our B location. So that'd move the agent halfway down. But if you do that, what you're going to end up with is that you're now, the next time we go through the loop, we've gone halfway along BA, and then we run through our update loop, and now our agent's in a new location. So we have a new B location, and the fish is still, we'll say it's still the same spot. So we have a shorter BA the next time. So that means the next time you take half of BA, it's going to be a quarter of what you started with originally. And so you're going to keep taking halves of halves of halves of halves, and your agent will be going more and more slowly towards the fish. And if mathematically, you actually would never get there. Your agent would just keep going slower and slower, never quite getting there. Now, in reality, in the game, especially if you have game logic related to, say, the overall shape of the agent touching the fish, the collider radius of the two objects would probably overlap fairly quickly. But you would still have this problem of the agent that goes really fast when they're really far away, and then slow down like slamming on the brakes, and it probably wouldn't be the sort of gameplay that you want. So what we're looking for is some way to standardize or normalize the speed of the agent relative to the direction we want to go from again, in the context of this update loop that we're running. So keep in mind, we're going to keep needing to sample these position vectors and calculate relative position vectors over and over, many times a second. So, the strategy that we should take on to improve our approach, rather than going halfway down the vector BA, we want to decouple the direction aspect of BA from the length. And so if you recall from probably your first look at linear algebra with vectors, we can perform different operations on vectors, such as normalizing or finding the magnitude of a vector. So that's a straightforward thing to do. We can take vector BA, which can be of some arbitrary length, and we can normalize it. And so that will give us direction. And so to normalize, we actually first need the magnitude, so we can use the Euclidean distance equation, so the square root of the sum of squares, and that works for 2D or 3D or even other dimensions. So, for instance, we could take the x and y component from vector BA, so the x times x plus y times y. Then the resulting sum we take the square root of. That gives us a magnitude. Then we can take the vector BA and divide by that magnitude, and that what that gives us is a normalized vector, or a unit vector. So regardless of whatever direction that vector faces, imagine that the positioning of the agent and the fish change, like maybe the agent is below the fish or above, left or right, whatever that is, we can calculate a direction vector that is always a length of 1. So if we have that unit vector length of 1, that means it's easy to multiply it by some scalar to come up with some new length vector. This allows us to, regardless of how far or close the agent is to the fish, we can come up with a standardized new resulting vector that is directed appropriately but has the right amount of movement that we want. So again, thinking about the update loop that we've discussed so far for our video game, we want to be moving a constant amount every frame, assuming our frame rate is running at exactly, say, like 30 frames per second. We want to move like a certain amount down the length of BA every frame. So the way that we can support this is to first figure out relative vector BA. Then we can normalize it, turn it into a unit vector, length of 1. Now we just need a little bit of information about our agent. That's how fast do they go. So this is like something that you just decide for gameplay. You want the agent to move a certain at a certain speed. So we have a speed scalar, and we can multiply that times the unit vector direction, the normalized BA. So speed times BA. And this just is because we can think of it as we have a direction that's decoupled from our speed. So if we multiply it together, then the result is a vector that includes both the direction and magnitude. And it will always be the right length or the right speed. Now, one thing you need to watch out for when you do this is that there's potential for a divide by 0 when you're normalizing a vector. So if you're doing this all by hand, like writing out the equation for calculating the magnitude using Euclidean distance, you'd have a potential to get a 0. And so this is something you need to be aware of and watch out for. When you're working with the game engine, there are usually things built in to help you avoid having these sorts of problems. But again, you should always be aware. All right, so at this point, when we've got the normalized direction, unit vector multiplied by the speed, we have this agent velocity. If we're going to perform our update during our game loop, we need to actually come up with a new location, a new position vector for the agent, and then assign that value. So we'll refer again to our high school level particle dynamics, and we can use the equation distance equals velocity times time. So we're trying to figure out the distance to travel offset from the current position B of the agent. And we have a velocity that we just calculated. We don't have a t value though. So we just need to decide what is our t value, and then we can figure out this offset from B. And assign that, let the game loop run, and then do it all over again. So where do we get the t from? So we could look at our simulation's target frame rate. If we know that our game engine is designed to achieve 30 frames per second, then we could just use the equation for period relative to frequency. So period is 1 over frequency. 30 frames per second is our frequency. So therefore, the period or the frame interval is 1/30th of a second, or 0.0333333, and so on seconds. So that is the value that we could use that for t. And in that case, the new B position, so B prime is equal to B plus the velocity of the agent that we calculated in the last couple slides. So that V agent times t. So adding that to B, because it's a position relative to B, it's like B is a new origin, so we need to offset from there. So that'll give us our new B value, and we will get our new position. But there is a concern here, and we're relying on 30 frames per second being very precise, but it might not be. In fact, you cannot always count on your simulation to run at exactly a desired frame rate. I have a Unity demonstration. I'm not going to cut over to it during this video. I'm going to have it as a separate resource. So be sure to check that out. But what you will see in that video is, depending on what content you have in your game, there might be so much work to do in your simulation that it takes that update process in the loop that you might recall. If that update takes longer than the 0.033 or something slightly less, because we also need to leave time for like the input polling and so on. If it takes too long, we might miss our schedule. And the work to do in a game loop varies according to what's happening in the game. So maybe if there's no enemies on the screen and the player hasn't fired a weapon that has lots of fancy projectiles going all over the place, maybe your frame rate is nice and steady. But as soon as 100 enemies come out of a zombie closet and you start firing missiles with lots of explosions and so on, the frame rate starts to drop. What that means is, if you were assuming that the frame rate was always the same and kept using that T value of 0.033, well, it could be incorrect. The end result is that any game object movement, like our agent, that's depending on that T value will either speed up or slow down according to the frame rate. And that's not what you want. You want to be able to standardize movement to be the right amount. So for a constant velocity, you want to see the right amount of displacement as that T frame time changes. So a better approach would be to ask the game engine, or just measure yourself if you're writing everything from scratch. You would measure the system clock time from whatever the previous frame was. That's the amount of time you're going to use as your measurement. And you're going to assume that that is the appropriate amount of time for rendering the next frame to appear. So it's like in the case of Unity, you can do time dot delta time, or I think it's delta time. If not, there's a similar command that will give you the elapsed time since the previous frame. And so you're going to want to use that in your simulation. Now, some game engines, including Unity, have what they call a fixed update. And this is where there's various tricks. They have a very precise update loop that's actually independent of the rendering update loop. The rendering is usually where you see the most variation in resource utilization, where you can have the frame rate go up and down according to what's on the screen. But there's still possibilities that you can have similar sort of varying load even in the update loop. So you have to start to worry about, in order to maintain the schedule, maybe just dropping things off the schedule based on some sort of priority, like, well, we're just not going to update certain things because we can't hit our target. My recommendation is to always assume that time is varying. The trade-off, though, is that you introduce at least these two additional multiplies, because you could actually roll the delta t into your speed. So when we had our normalized BA vector times the speed of the agent, we could have just embedded a fixed t size into that pre-computed and not have all these multiplies. This used to be a big deal on old, like classic computer platforms, games on 286 level computers in the late 80s. just did not have the processing power to be able to easily have these extra multiplies for the delta t. If you could get rid of even a few multiplies, it might mean the difference of an interactive game or not. All right. So yeah, look for the video that will be posted separately with the Unity demonstration. We'll look a little bit more at this issue. All right, so now we have an agent that has this ability to do this basic movement. One thing that I wanted to point out is that we can think of the position of the player as this static information. In fact, in the Game AI book, the Millington book, he refers to this as statics. So the position would be one of the statics. And we can also add orientation. We haven't talked about orientation. We're going to actually look at that in just the next slide. But those two, the position and orientation, we can refer to as statics. And those are things that can be updated by, say, velocities or accelerations. So in the case of orientation, the movement that's been presented so far, we don't need really to have orientation to support the movement, especially if our agent's position or orientation is fixed. So, for instance, if we have a 2D game and the agent just needs to always have the eyes at the top of the head and the mouth at the bottom of the head, we would just leave it in that orientation regardless of whether it's going left, right, up, down, and so on. So that it might not be important to rotate. But in other games, it could be important. So in those cases, we might want the agent to face in the different directions. But most often, this is going to be facing the direction of travel. So if the agent happens to be going up, well, we're going to rotate so that the forward direction of the agent is in line with the velocity of movement. And then, of course, left and right, we'll just rotate to match. So we're going to look at how we're going to do that. But first, let's consider some more aspects of our coordinate system. So I mentioned before, we have this 2D vector space. We're probably going to be working with the coordinate system of the game engine, and especially the implications of the need for graphics rendering. So in 3D graphics, you tend to have X and Z be the horizontal plane, and then Y is up. So even though we're talking about a 2D coordinate system, it would make sense to have X and Y be our coordinates. It's actually going to be X and Z in most cases. And because it's a 3D coordinate system, we have this issue of left-hand or right-hand coordinate system. And that basically just the orientation of the X, Z, and Y changes depending on whether you're left or right-hand coordinate. So you may, in some cases, have Z positive be forward or negative Z is forward. And for a 2D game or what we might call a 2.5D game, our agents or the 3D graphics model of our agents will be oriented such that the feet will be on the XZ plane, and standing upright, the head will be in the Y direction. And any rotations that the character makes, since it's bounded by gravity, it doesn't really make sense to rotate in a direction that would make the character tend to lay down. So we want to keep the character upright. So we're going to actually be rotating the character around the Y-axis. So we have just this 1 degree of freedom rotation that we're concerned about. And then our movement is in either the X or the Z direction. So that tends to be the standard for thinking about how we're going to move an agent around. Even if it's a 3D game where jumping is possible or falling off of cliffs and so on, we're still going to have this 2D representation for any sort of decision making. Now, in the case of our rotations, we do have to consider, what are we using as forward, and so that will either be positive Z or negative Z direction usually, and we have a choice here. We can decide that we're measuring angles relative to the forward vector or relative to the x-axis. If you look in a math book, you'll see rotations relative to x. And so that might change the terms in terms of trigonometry, whether the x term has got the sine or the cosine versus the z can change. But and then each game, if you're using game engines, they'll each vary on what the angles are measured from. And better is not that big a deal. You can usually just involves either flipping what sine and cosine, or in the case of left hand, right hand is changing the negative or positive sign to work things out. And if you just think back to your trigonometry, get out a piece of paper and draw out everything. If you don't know what the game engine uses, of course, you need to look that information up in a reference to know what coordinate systems you're working with, but it's something that you can sort out pretty quickly. So normally you would store in terms of the statics for your agent. You're going to store, again, position and orientation. Orientation you probably will store as a unit vector. It's usually easier to work with unit vectors, but you could also store it as an angle. And you might also just pull it from the graphics representation. So for instance, in Unity, orientations are represented by quaternions. So you could possibly pull that information out from there. In Millington's book, he stores this information independently in the statics. So one thing you might want to do is, if you are storing the orientation as like a forward vector, so an x and y unit vector for the facing direction or the orientation, you might want to go back to having an angle relative to whatever you're measuring from. And so this is also something you could just work out with the trig equations that you're familiar with, and you could certainly do that. But a very common convenience function you find in many computer science type libraries, APIs for graphics, is this atan2 function. And atan2, it rather than going ahead and dividing the two terms that you would come up with normally, you provide the numerator and denominator separately. And the reason you do that is because you can have negatives that cancel out. And those negatives would actually indicate to you what quadrant of the graph in the coordinate system, what quadrant the vector for the angles that you're calculating, which way is it going. But if you cancel them out, it creates this ambiguity, and therefore you don't truly know which way the angle is facing in like 180 plus or minus 180 degrees. So atan2, since it preserves the negative for both A and B, not letting them cancel out, it allows some conditional code within the atan2 implementation, so like an if statement can determine, well, okay, the resulting angle that we're reporting should have 90 degrees added in addition or not. And so it's just a convenience function that you should be aware of as a game developer. All right, so we can add orientation to movement now. And really all we need to do is just use our normalized BA vector, and that will tell us the orientation to face. But that only works if BA was not 0 length. So we actually need some fallback logic. What do we do if it is 0? So that would mean like what if the agent has already gotten all the way to the fish? If that is the case, then our fallback could just be, well, recall that we have the statics, that with this metadata we're storing for our agent, and this is going to be preserved from frame to frame. So anytime you look at your statics, you know the information that was used from the previous frame. And so you just use the last known good orientation if that BA was 0 length. And so in this case, we just set the orientation and in our game engine for the game object. And this is going to vary with the game engine. Like in Unity, there's some lots and lots of high-level linear algebra functionality already built into the system, makes things pretty straightforward. You can actually just grab the transform, which this is mathematically represents the overall pose of the game object. You can grab the transform and you can directly set the forward vector, and it'll automatically do everything it needs to do once you provide the forward vector to rotate the object so that it's facing the correct direction. Otherwise, you might need to do this yourself. So you might have your standard 3D game. You're going to have these 4x4 matrices that represent your transforms for each game object. So this will be a homogeneous affine transform. So homogeneous representation is used because it's important for the projection process, putting the 3D information onto the 2D screen. And affine transformations preserve lines and parallelism, which is usually something that you want when you are moving objects around in the world, translating, rotating, and if you have uniform scale. So those are all the very common sort of gameplay operations to perform. And so your typical game engine is going to provide a lot of that functionality for you. If you happen to be rolling your own, though, you will have to concern yourself with the pose represented by this 4x4 matrix. But that can be done, and you can apply the rotation that is based on facing that unit vector, that BA vector direction. We could have some slightly fancier rotation, because if you think about what's happening here, we're picking the direction to go. So we're figuring out a velocity, and then we're just always setting rotation immediately to the velocity. So this could create scenarios where if positions change suddenly, like our target position, you're going to have this over a single frame of the simulation. You're going to just snap the orientation of the game object to immediately face a new direction. But we could add sort of a little aesthetic sort of animation that we calculate by hand in the rotation. So if we know from our statics preserved our last known orientation, we could apply an angular velocity to rotate towards whatever our new direction to face is. So over several frames, if the overall angle exceeds our angular velocity maximum speed, we're just going to rotate as quickly as we can in that direction. What that will do is it will make something that looks more realistic in terms of the game. You'll see the character might start to move in a particular direction, but it'll take a while to whip around and face where it should be facing. The downside to this, though, is that it might look awkward in terms of like sliding sideways. So your agent will not be turned all the way to face where they're going, and depending on what they look like, maybe if they have feet or some sort of expectation on the part of the player, like they think that this agent should always walk in the direction they're looking, but then they're kind of sliding to the side before they get turned all the way. That might be a little jarring, but so that's the trade-off of using this approach. All right, so we have just defined basics of kinematic movement, and in particular, we have an algorithm for seeking. So this is where an agent is seeking out a target. So a kinematic object knows its statics, and that is the position and the orientation, and it updates its position its position and orientation, updated according to whatever the kinematic algorithm or strategy is. So, like seeking, we'll be coming up with a velocity, and then that velocity is used to update position and define the new target orientation. We might have a secondary step of applying an angular velocity to the orientation to then adjust the orientation, or we might just do the simpler approach and just snap orientation. We might not even worry about orientation. Again, there's some games that the character is just always going to maintain a fixed orientation but still move around. Those would be much more simple 2D games, though, most likely. So a bit about implementation. So we've seen an algorithm represented in just a handful of simple equations. Of course, there'd be a bit more in terms of coding that would need to take place to implement this. And if we were to do so, one consideration that we might take is that we might decouple the calculation of our velocity. So say the case of seek, we come up with a velocity that takes our agent towards the target. We might just come up with the velocity and then assign that to an agent. And then when it's time for the agent to update, well, they know their statics, which is position and orientation, and it knows this desired velocity. So it would apply, like it do its own update, kind of thinking in an object-oriented sense. It would apply its own target velocity to its statics and then generate those new values. And then the agent would be drawn onto the screen with those new values. So I'm mentioning this because, well, one, it is the framework for agent movement that is in Millington's AI for Games uses this sort of approach. But also works well as we look at more complicated sorts of movement, such as steering behaviors. It makes sense to decouple these desired movements, whether velocities or accelerations and so on, decouple that from the actual final result. So let's consider a few other possibilities for movement within this framework that we've defined so far. So we've looked at seeking, but what about fleeing? What if the fish was dangerous and our agent wanted to get away from the fish? Well, in that case, this is a really straightforward one. It's almost for free. We can just flip the calculation of a relative position vector. So rather calculating from B to A, we're calculating from A to B. Everything else, though, is just the same. We're just we're still going to be offsetting from B, even though we did the relative vector from A to B. We can add that once we've done the normalizing and multiply by the agent speed and so on. We add that still to the B position. So we're just flipping the subtraction part of that relative vector calculation. And that will give us a very simple kinematic fleeing behavior. We could also come up with a variation for arriving. So the difference here is that we want the agent to stop upon arriving. Now this introduces a problem if we don't make some adjustments to the algorithm. So as the agent gets closer and closer to a target, so from B to A, that position is going to get smaller and smaller. And as you get smaller and smaller, we're taking a very tiny vector. In fact, it'll get shorter than a length of 1. And then we're normalizing it back to a unit vector. So we're dividing by the length and so on. It's going to get super tiny. And as that happens, related to various issues, maybe the agent doesn't move exactly along the path the way you expect if the agent gets bumped, or more likely just the numerical accuracy of your floating point representation, that's going to start to introduce some noise. So the direction you're asking the agent to move is going to kind of flutter around, aiming a little to the left or the right of the target position. And as it gets closer and closer, it might never actually land, and it might be impossible for it to land exactly on the point. And what happens is you're still, when you try to do any sort of comparison, say that vector A equals vector B, those two positions to be an exact match, they might just never match. And so you're going to keep having the agent zigging and zagging and wiggling, trying to move towards the goal at maximum speed all the time and just never getting there. So there's a couple things we need to do in order to actually get an agent to arrive. So at minimum, we need a capture radius that's large enough to wash out any of those rounding error type issues that you might run into. So rather than having the B be exactly A to say they're arrived, you would say that some capture radius distance from A, if that is greater than the distance or the magnitude of vector BA, then we know that we've arrived. And that can still be pretty small. Like visually, the game player might not even notice the size. But it'll depend on your game. The other thing that might be nice is to have the agent slow down upon arriving. So that would be reasonable behavior for arriving at a location, not to just instantaneously slam on the brakes. So we could actually use both of those approaches. So in order to pull this off, we will modify the seek algorithm that we have looked at so far. And we'll do so in the following ways. First, we are going to check the magnitude of vector BA and see if it is less than or equal to the capture radius. If it is, then that's going to trigger an event that the agent has reached the target. So we'll probably have the agent stop moving, and maybe there'll be some sort of message or a flag gets flipped to denote that the agent has, in fact, finished the job of seeking. The other thing that we'll do is to have the slowdown for arrival. Again, think about how this takes place over multiple frames. So we're going to take our vector BA and we're going to divide that by a time to target. So you can think about vector BA, we can actually think of it as it's like a velocity. It's the speed you would have to go in order to teleport from wherever you're at in one frame. How fast would you have to go in order to get there in the next frame? So it's not only a relative position vector. We can have different perspectives of this. So for dividing by this time, that's telling us, well, how long, or rather, how fast would we have to go to get there in 0.25 seconds? So then, once you've figured out, or what what's the velocity you have to go to get there in 0.25 seconds. And once we know that velocity, we can take the magnitude of it and compare that to whatever the agent speed is. So that's like a speed limit. We don't want the agent to start going faster than that. So if that resultant vector is less than the maximum speed allowed, that means we're slowing down to reach our target. And so we'll use that for our, instead of the normal way of calculating our velocity, we'll just use that, the BA divided by the time constant. And assuming we keep getting closer, then we're going to keep going slower assuming we keep using the 0.25 seconds, we'll go slower and slower. And so usually that's not an issue relative to the capture radius, but you might, you might actually want to adjust the time, but in practice that isn't necessary. You just keep using the 0.25 seconds and calculating. Otherwise, if that BA divided by the 0.25 gives a velocity that's too fast, so faster, the magnitude is faster than the speed of the agent, in that case, we'll just use our old strategy and calculate V agent as before, and just go full speed towards the target until we trigger that that slowdown that's handled by the BA divided by time to target. Another algorithm we might want is to have, let's say, rather than seeking or arriving or evading, we just want an agent to sort of aimlessly wander around, like maybe a villager, a non-player character NPC in a game. We just want them to wander around a bit. So a simple way to implement this would be to actually rely on the orientation rather than any particular target. We don't have a target in this case to go. So instead, we're just going to refer to the orientation in the statics from the previous frame. And we're going to just say, well, we're going to keep going in that direction, except we're going to nudge the direction a little bit this way or that, according to like a random number generator. But we don't want it to be completely random. Otherwise, the agent will just move in crazy zigzags, tending to stay in the same place. And if we have rotation changes that are too extreme, it's going to look really disconcerting and certainly won't look right for most games. So instead, what we'll do is we'll take our orientation. We're going to add a little bit to the angle, either a little bit positive or a little bit negative. So we'll rotate more or less, depending on this random number generation. So we actually, what we would like is to generate a random value between -1 and 1, but that tends more often than not to be at 0 or around 0. And so there's different approaches you might take to this. You might think to use like a normal distribution, for instance, and then you calculate out all the terms and so on, set the standard deviation. But a simple trick you can do to get this kind of zero biased random between -1 and 1 is assuming you have your standard sort of random number library that gives you a value inclusively between 0 and 1. You just call that twice, you get two values, and subtract one from the other. So that'll give you something in the range of -1 to 1, but the more likely value, or most likely to occur, is going to be around 0. So this is just a nice little trick you can use. And then you add that resulting value, this between -1 and 1. You add that. You might have to, depending on how your angles are represented, whether it's in like radians or degrees, you're going to need to multiply it by an appropriate scalar to for the right amount of rotation. And then you can just add that to the orientation. And then new orientation, that gives you your new direction to go in vector form. So if you have the orientation in vector form, so like the sine and cosine or cosine and sine of the angle terms, then you can use that times the agent speed, and that'll set the velocity as well. And so we get this nice wandering behavior over many frames. So another thing we might want to do is follow a path. So we can imagine having a series of waypoints, and we want to visit the first one, then the second, the third, and so on. So in this case, we can just use seek for each waypoint. We probably want to not be slowing down for each individual waypoint. We want to go as quickly as possible. And we also might consider a special case of when we know we're on the last waypoint, we'll use the arrive algorithm for the last waypoint, maybe to get a nice stop there. So even though we'll be using seek, we probably do want to use the capture radius here, especially if there's some game logic that says keep trying to go to the waypoint until it's been visited. You want to use a capture radius to define when visiting the waypoint is complete. And so that'll avoid the wiggling or missing the waypoint and having to backtrack and so on. So one issue here is if your capture radius is big enough, this algorithm will mean that the agent is really never on the path completely. So hopefully this image here gives you an idea of why that is that as your agent's moving along, as soon as the condition for having met the capture radius is achieved, then you've initiated the next waypoint. So you've never actually gotten your agent all the way to the center, and the agent makes no effort to get back on the line. They just sort of go along adjacent to a line if there is a line segment implied by the sequence of waypoints. So if you intend for your agent to go make a best effort to stay on a line, they're not going to curve their way over to the line. You need a more complicated algorithm. There are better approaches to this. We will revisit this when we look at steering behaviors. And speaking of steering behaviors, so far this basic movement that we've covered with a kinematic movement, it's functional. It gets our agents moving, but it doesn't look very natural. So you can imagine like our following waypoints, it's going to have a very awkward zigzaggy pattern to it because of this instant change in velocity that occurs. We don't have any nice smoothing or accelerations. We still, even if we try to animate the orientation of the agents, it's still going to have like this moonwalking look in certain scenarios. Just generally, it's too aggressive, turning too quickly. There's no sense of momentum that we might desire in our game. And so many of these sorts of issues are addressed in steering behaviors, which will be a future topic of more advanced agent movement. But this video is going to, it sets the stage for just a basic understanding of character movement. We're going to actually look at other aspects of our agent moving around an environment, especially related to path planning, before we get back to steering behaviors. So we're going to stop at this point, and if you have any questions, feel free to reach out. Hey guys, I promised a demonstration of frame rate dependency using Unity. So I'm going to show you that in this little video. It's meant as a addendum to the game engine lecture. So I'm going to switch over to Unity here. I've got a project that I've had for a while now. So in this project it's got a little simple rolling ball, kind of like the rollerball type assignment, but it's got a couple little satellites that rotate around the ball, and they're animated each in a different fashion, which we'll check out in a second here. So the way that these animations of the rotation work is that one of them is animated in a way that is just a fixed amount of rotation, a fixed number of degrees per update, if you think in terms of like the game update loop. And the other one rotates according to how much time has elapsed. The game that I'll show it's configured to run at 60 frames per second as best effort. But it's possible that it won't hit 60. So if you recall, I mentioned how in game sometimes the amount of content that's in view there can be so much content that you start to miss your target frame rate, and when that happens, you start to just wait longer, or it takes up time to complete all the tasks, and then by the time that you do finally send the information to the display, you're well past schedule, and essentially your frame rate drops in that case. And so we'll see what happens. So let me just go. I'll go ahead and play this Unity scene here. So you can see there is a ball, and then there's what look like two Tic Tacs, a red pill and a blue pill. And so I can move around a little bit. You'll notice the frame rate is really close to 60 at the moment. So I haven't started rotating the pills yet, but let me hit a button here, and you should see them rotating. Now again, they're each using a slightly different method of rotating. And they're starting to get out of sync here, you'll notice, but generally they're pretty close together. You do see probably the frame rate counter is occasionally dropping to about 58 frames per second and then back to 60. And so we're getting a little out of sync here. But I've got a more extreme example that I can show you, because right behind me is a massive particle system. And it's generating huge numbers of particles, well past the point like you would ever use in an actual simulation. And so that causes some big slowdown in the game. So let me start to rotate around, and suddenly this will begin to become in view. And you can see there's so many particles, you can't even tell that there's individual particles. It just looks like a big cone shape, but that's like a fountain of particles going up. You'll also notice the frame rate counter. Look at that. It's dropped all the way down to barely over 20 frames a second. Now look at the two pills here. So the blue pill is spinning around. The animation is choppy, but it's still maintaining its rate that it was before, whereas the red pill it looks like it's going much slower. So it seems to, and then as I rotate back and we hit 60 frames a second again, see how it appears that the red pill accelerated back up to full speed. And so let's look at exactly how the code is written for these two objects. And so in fact, it's actually the same script. Let me bring that up. All right, and in this script, we've got code here. Let me actually, I'm going to pause and see if I can get this font bigger. Just a second. Okay, we're back again. Got a bigger font finally, and so you should be able to see this code. This is a mono behavior attached to the red pill and the blue pill. And you'll see that in this code that there's actually not a lot going on. There are a few member variables, and then there is update. And so the member variables that are important here are these two constants here. One is a constant number of degrees, which is currently set to a value of 1. And there is also a degrees per second value of 60. And so then if we scroll down, you see an update. There's a little bit of code to handle key presses. So there is B is what I hit to begin the rotation, and R I could actually reset. But the actual part that's performing the animation is really quite simple. It's one of these two lines. So there's if is dumb mode. This is doing a this dot transform dot rotate. So it's applying a rotation to the transform that defines the pose of the object, and it's performing a rotation around the up vector, up world vector, constant number of degrees. And so update is called as part of the game loop. Update is just called at the point that we're preparing for rendering. And then alternatively, what I would say is the better version is to do the same rotation around the up world vector. But this time you'll see that we're multiplying degrees per second times the time dot delta time. And so the time is a Unity manager that provides services related to time. And so one thing it does is it measures elapsed simulation time. So time.delta time tells us how much time since the last update. And that's a floating point value in units of seconds. So it's going to be a fractional value, pretty small if we're hitting close to our 60 frames per second. So if we're hitting precisely at 60 frames per second, if we're doing the first mode, the constant number of degrees rotation, that will be equivalent to the second one. However, as you've already seen in the demo, we cannot maintain that frame rate reliably. And so the impact is that if you have something like an animation, maybe programmatic control of a game object such as this, and it could be other things than rotations. It could also be translation. So if we could have a linear velocity, and it could be accelerations as well. And really any derivative of motion could be affected. And there's lots of things. So I mentioned in the game engine lecture that there are some things that might not be intuitive to you that have time dependency, such as I had an example for an artificial intelligence sort of decision making, and so you should always be cautious about this. Now, in Unity, there is actually there's different parts of the update cycle or parts of the game loop in which you can extend functionality. So you're extending functionality of the game engine when you write a mono behavior script. And so your calls to update, that's an extension. So like in the case of this particular script, we're adding programmatic animation of the rotating capsules. And so there's the update call, and that's where it's associated with the render updates, which do make a best effort to hit a target frame rate that we have set. And by the way, in the project I have code that sets the target of 60 frames per second. But there's also other callbacks that you could use for extending functionality, and one of them is called fixed update. And so fixed update is different than update in that Unity tries to hit this very precise update rate, and the idea there is that you could potentially have these constant translations and so on. And so actually the physics engine runs there. And now the problem is well, what if something happens? What if suddenly there's a lot of extra complexity that drives the computation to the point where the schedule cannot be maintained. And so that's the tricky part to deal with, is because it's really hard to guarantee computational complexity in this case. So in many cases, when you have these sort of real time scheduling, so like a fixed update, you actually start to abandon doing work. So the game engine would decide. So if you had something that was part of the fixed update cycle, but complexity got too high, Unity, for instance, might just stop updating some objects in the cycle, or splitting things up and say, oh, I'm only gonna, for this particular tick of the fixed update cycle, I'm only gonna update half the objects and then start alternating, something like that. The advantage you get if you could reliably maintain a fixed update schedule is that you avoid this multiplication. So if you think about the code that I've got on the screen here, if let's say we have lots and lots of objects and they all have time dependencies, so that means we have a whole bunch of examples of a multiplication times time.delta time. And it might seem trivial, just a little small computation, but they can add up across lots of objects. And so if you could avoid them, that would be desirable. In fact, a lot of early games, especially of the 2D variety, back in the 8-bit era, those games, it was the computation that the processor could do was a precious commodity. If you could avoid doing these multiplies by elapsed time, then you could gain a lot of performance in your game. And so, in fact, that's how a lot of games did work. And this was fine in a lot of cases, because 2D games are a lot different than 3D in that there's only so many. There's like a well-defined limit of how many sprites can be on screen at the same time. It's easy to constrain how many, like what's the maximum number of enemies that could be on screen. And by having those sort of constraints, it's easy to plan for the worst case and build in a buffer that can absorb up to the maximum that is possible in terms of scene complexity. So your typical 2D game, whether it involves scrolling or various amounts of enemies, we could easily define this cap and hit a schedule with essentially a fixed update approach and constant translations or rotations. Anything that's time dependent could just be like these fixed increments, like what is labeled the dumb mode in this Unity example. And that worked fine as long as the computer that you were running on was the same in all cases, like the frequency that the computer ran at. So like 33 megahertz, 386 or something like that. The problem with this, though, is if the game is deployed to other platforms, then you can run into problems with speed. So if you had a computer that instead of 33 megahertz, if you had one that could double that and go 66, the game would run twice as fast. The animations would, the movement of game objects or sprites along the screen they'd be too fast. And so this was something that had to be dealt with. More capable games may have recognized the actual speed at which the computer ran, and it could at least make an adjustment to these constants for like the constant amount of translations, for instance. But without that, if there's an older game and you wanted to play it, even still the case today, you would actually need to run something on your computer that slowed it down. And so in fact, there's this little program I used to use. It's called MoSlow. So you would run this sort of in the background of your computer, and it just would burn up cycles, and therefore your game would be able to hit the frame rate as if it was on slower hardware. And more recently, when you're running on emulators such as DOSBox, there are settings in DOSBox where you can play with how fast the emulated or simulated processor runs, and so it's important to get that right because of exactly this issue. Many of those early games wanted to avoid multiplying by the amount of time per frame. So in terms of your own work, many of the subsystems of Unity already take into account this sort of incremental nature of time. So if you're using the animation system for like 3D skeletal animation and many other features, then you don't have to worry about it. But if you're doing programmatic manipulations, like I'm showing here, so with the rotation, you want to make sure that that you're taking into account the elapsed time, this multiplication by time.delta time. And again, that applies to translations and rotations, and whether it's an acceleration, or velocity, and so on. You need to make sure you involve time correctly. Alternatively, you could consider using fixed update, but you need to be cautious because there are some things that really do need to be on the fixed update, and some things that don't. And so you don't want to put too much into the fixed update cycle, because you might get to the point where you cannot reliably run the game. And just be aware that there's always this potential for wild swings of resource demands, especially in a 3D game. Just the nature of the way the view frustum works and culling works, that sometimes you can be looking at a part of a scene that's very low detail, and sometimes parts of the scene that are very high detail and therefore much higher load. So you need to be careful about that. So hopefully you found this informative. I'll run it one more time here just to demonstrate again. So yeah, we got the sphere. We're looking away from the particle system. That's the high demand. So we're hitting roughly 60 frames per second. I'll hit B for begin. We've got these fills rotating around. They're almost aligned. And then I will just rotate around slowly. And eventually the view frustum is going to get close enough to the particle system. Right around in there was close enough that Unity said, okay, it's time to start dealing with the particle system. And so we hit this huge frame rate drop. And that's just because just looking in different directions in the scene changes the resource demands of the update before we can render. And so I can reset, I can align them, but very quickly they get apart because the red pill is just using a constant amount of rotation, but now at a slower frame rate. The end result is a slower relative movement. And then if I swing back again to where the culling can ignore the particle system, we're back to 60, and you can see that there's essentially the two capsules moving in lockstep. So you just to close out this. It's important to realize where you've got these frame rate dependencies, and you really need to address them by making things that are time dependent involve that delta t in the calculation, so that you can make the animations or whatever other process we're talking about that's time dependent, making sure that it's consistent across different platforms, but even on the same platform, being consistent across different frame rates. All right. Hopefully that explains that issue, and I guess we'll close out here.